On April 13, 2026, a Chinese company called Geely held a press conference in Hangzhou and announced that their new engine had hit 48.41% thermal efficiency, a number that Guinness World Records independently verified and that engineers across the industry had spent decades insisting was physically out of reach for a mass-produced vehicle. To understand why that number matters, you first need to understand where your fuel actually goes when you drive. When a conventional Toyota or Volkswagen burns petrol, roughly 30% of the energy in that fuel reaches the wheels. The other 70% bleeds away as heat through the exhaust, into the engine block, through friction between moving parts. Engineers have been chasing that wasted energy for over a century, and the best any mass-produced engine had achieved before Geely's announcement was around 42%, which is where Toyota's dynamic force engine and Nissan's e-power system had both landed after billions of dollars and decades of refinement. The industry largely concluded that 42% was close to the ceiling and that pure electric vehicles were the logical next step. What makes 48.41% so remarkable is how far past that ceiling it sits. Formula One racing engines, built with no cost constraints whatsoever, typically achieve around 50%. Geely is now making a mass production car engine that operates in the same conversation as F1 power units, while selling it in sedans and SUVs at consumer price points. Before we get into how Geely did this, it is worth understanding what BYD did first, because that is where the shift really began. BYD looked at the conventional hybrid architecture and asked a straightforward question: what if the engine never actually drove the wheels? In a conventional hybrid, the combustion engine and electric motor both power the wheels simultaneously, which means the engine constantly changes speed as road conditions change, drifting away from its most efficient operating point every time it does. BYD's DMI system removed the engine from direct wheel drive entirely. The engine runs at a single constant speed as a pure electricity generator, always at exactly the RPM where it is most efficient, while electric motors handle the wheels. The result was 46.06% thermal efficiency. The global automotive press was genuinely stunned because Toyota had taken roughly 20 years and several $billion to gain the 5% that brought them from 36% to 41%, and BYD had done something comparable in a fraction of the time. Geely took that foundation and kept going. Their efficiency progression reads like a sustained campaign: 43.32% in 2021, 46.5% on the BHE15 platform, 47.26% last year with AI integration, and 48.41% announced in April 2026. A percentage point gained per year consistently, while the Western industry was busy declaring the combustion engine essentially finished. The engine at the center of this is the BHE series, purpose-built for hybrid use rather than adapted from a conventional design. Some of the specifications tell you how obsessively it has been optimized: a compression ratio of 15.5, which would cause catastrophic knock in a conventional petrol engine, peak injection pressure of 500 bars, diamond-like carbon coatings on friction surfaces, and precision grinding that reduced friction losses by 16.3% versus the previous generation, contributing 0.4 percentage points of thermal efficiency on its own. The engine went through 15,000 hours of bench testing before production, the equivalent of 4.8 million kilometers of driving. The combustion system is what Geely calls the wind ride tornado. The problem it solves is this: in a conventional cylinder, air and fuel do not mix evenly when they enter. You get fuel-rich pockets and fuel-lean pockets, which means when the spark fires, the flame propagates slowly and unevenly across the chamber, bleeding heat into the metal walls while it travels. Geely redesigned the intake channels and added a duckbill intake geometry so that incoming air enters as a high-speed spinning vortex. When the spark fires into that uniformly mixed rotating charge, the combustion happens almost simultaneously throughout the entire chamber, rather than rippling outward. The energy release is fast and concentrated, driving the piston down before heat has time to escape into the engine walls. Running at high compression and intense combustion creates a knock problem, which is precisely what has kept engineers stuck below 42% for so long. Geely's answer was to split the cooling system into two completely independent thermal zones. The cylinder head, where combustion happens, is kept aggressively cold, which suppresses premature detonation and allows the engine to run at that 15.5 compression ratio safely. The engine block below, where the pistons slide, is kept deliberately warm because warmth reduces oil viscosity, and thinner oil means less friction. Cold at the top for compression, warm at the bottom for friction reduction, both happening simultaneously in the same engine, controlled by an electronic water pump that adjusts coolant flow dozens of times per second. In a conventional cooling system, those two objectives directly conflict because everything runs through one circuit. The drivetrain that connects all of this to the wheels is what Geely calls the 11-in-1 EDHT. It packages the engine connection, generator, two electric motors, high voltage inverters, and thermal management hardware into one compact housing that is 13.5% lighter than comparable conventional hybrid drivetrains. There is no torque converter, no multi-plate clutch pack, no hydraulic fluid circuits. For about 80% of driving, the combustion engine has no physical connection to the wheels at all. It generates electricity, which either charges the battery or powers the electric motors directly. The driving experience is essentially that of a full electric vehicle, silent, smooth, instant torque response. The only time the system connects the engine mechanically to the wheels is at sustained highway speeds above roughly 80 km/h, where routing power through the electrical conversion chain actually wastes more energy than a direct connection, so the system locks engine to axle automatically. Managing the whole system is Geely's AI Cloud Power 2.0, which processes navigation data, ambient temperature, humidity, and road gradient 50 times per second. It reads your route, identifies the hill coming up 3 kilometers ahead, and decides whether to charge the battery on the climb and coast the descent or do it in reverse. The system is planning your entire journey simultaneously, rather than reacting to what is happening right now. The combined result of all of this is a Guinness certified fuel consumption figure of 2.22 liters per 100 kilometers. In real-world driving, the Geely Prius sedan achieves around 59 mpg and the Xingyu L SUV around 50 mpg. A full-size SUV at 50 mpg, refueling in 4 minutes at any petrol station on the planet, with a range of over 2,000 kilometers on a full tank. That is the practical case this system makes against pure electric vehicles in markets where charging infrastructure is still thin, or where long distances between stops make range anxiety a real problem. The system went into mass production immediately. Pre-sales for the Xingru F-im sedan and Xingyu L F-im SUV opened on April 19th, with the Preface, Manjaro, and M-Grand lineup following through 2026. For the Western and Japanese automotive industry, the challenge this creates is not really about specifications. It is about the assumption that was wrong. The prevailing belief was that 42% was close enough to the practical ceiling, that hybrids were a transitional technology worth only incremental investment, and that full electrification was the only destination worth serious engineering focus. Geely has now improved their thermal efficiency by over 5 percentage points in 5 years, with each annual improvement arriving while legacy automakers were redrawing their electric vehicle roadmaps. Closing a gap like that requires rebuilding engineering pipelines from scratch, funding sustained research over years, and accepting that the previous answers were not actually limits. That is a difficult ask simultaneously with investor pressure to go fully electric. The combustion engine was invented in Europe and refined to what the world considered near perfection in Japan. The world record for combustion engine efficiency now belongs to a company that had no serious global automotive presence 15 years ago. Formula One teams spend hundreds of millions of dollars per year to achieve 50%. Geely is at 48.41% in a family sedan. What do you think that means for where the car industry actually ends up?